We have seen in the last few videos that the worst case complexity of a find operation can be brought down to order log n, where n is the number of nodes in that particular tree, by ensuring that whenever we are merging together two connected components, we always make the smaller component, or the leader of the smaller component, the child of the leader of the larger component. It turns out that there is actually even more scope to further improve the complexity of a find operation. And to see that, let's go back to what happens when we try to find the leader of x. We basically start from x and we check whether the parent of x is a different node from x or whether it is the same as x. If it's a different node, as you see in this diagram, we walk up to the parent and then we check its parent. Is its parent the same as that node? No, it's another node, and so we walk up to that parent and we keep walking up like that until we reach the root of this component, which has the property that its parent is itself. And once we hit that property, we know that we are at the root, and so we return the value of that current vertex where we are. Now, it's possible that we might have to do a find operation on x or one of these interim nodes many times in the future. So what if we did a little bit extra work when we did find on x the first time to make sure that any future find operations on x or any of these interim nodes could run in faster time? So what could we do? Well, once we know what the root of x is, why don't we directly link x with its root, which means we divert this parent pointer from x to not point to its former parent, but to now directly point to root of x. And we could do the same thing for all the interim nodes that we had walked through when reaching root of x. What if we could change their parent pointers? Let's say we change the pointer of this node and this node also to point directly to the root of x once we know what the root of that connected component is. So the advantage of doing this would be that any future find operations on x or on this node, let's say it's y, or this node z, will take a constant amount of time, because we would no longer need to walk along this entire path to reach the leader of that component. We just go to the parent, and the parent is already the leader of that component. So by doing a little extra bookkeeping after we have determined root of x, we can actually save time for future find operations. So what we'll do is we will re-implement find in a way that we first do this walk as before, and then once we have determined who the leader is, we come back to x, and then we start changing these pointers from x, the parent of x, the parent of x, and so on. Basically all the interim nodes, we change their parent pointers to point to the leader directly. So effectively the path from x to root x gets compressed for future find operations, and because of this technique is called path compression. So path compression is basically the process of doing some extra work when we are doing find on x to basically come back after we have determined who the leader is, to come back and to compress the path, the entire path from x to root x, so that all the nodes along the path now have direct pointers to root x. The nice thing about path compression is that once we re-implement find of x to incorporate path compression, it doesn't affect the rest of our union find code. So we will preserve the same code that we had for doing a weighted quick union. We are just changing the underlying implementation of find of x to incorporate path compression. So now find of x has to basically do two things. It has to return the root of or the leader of that component as before, but it needs to do that after doing path compression. So there is a side effect that doing a find is going to have on these paths. We are going to compress these paths and then finally return at the end of the function who the leader of the component is. So I'm going to implement this recursively using the lazy managers analogy again. So what if I am in the base case where x is already the root of x, right? So if it turns out that x is its own parent, that means x is the leader of its component, then I don't have to do any path compression. I just have to directly return x. In the recursive case, I'm not already at the root. I'm somewhere below. So let's say this is where I am. This is where x is, and let me add in the edges that we had before I did the path compression, just to show how this code would work. So what I do is I delegate the work of finding the leader to someone else. I know at this point that my parent is different from me, but I feel too tired to walk up all the way to the leader. So I'm going to call a subordinate and hand them over the identity of my parent and basically delegate to them this subproblem of figuring out who the leader of this entire component is, starting from the parent of x, which is the node that I handed to my subordinate. So basically I will make a recursive call delegating the work to my subordinate, finding out who the leader of this component is, but the subproblem that I am assigning them is slightly smaller than the overall problem that I had. My problem was to find out who the leader of x is. I did a little amount of work. I figured out that I'm not already at the root. My parent is different from me. Now I'm going to call someone else and give them my parent and ask them to do that remaining work of walking up that entire path up to the root and just come back and tell me who the root is. So they're going to return to me a value which is going to be the root of x. Now if I didn't have to do path compression, I would just return this root x, which was handed up to me by my subordinate. But I also have to do path compression. So I'm effectively going to remove this edge from x to its parent and instead pretend that the parent of x is now going to be directly the root of x. So what I'll do is I'll reset the parent of x to be root x before returning root x to whoever called the find function. Now what's interesting about this is that because I did the work of diverting my parent pointer to root x, everyone in my hierarchy must also be doing the same thing. So before returning the root of the component back to their superiors, they would have redirected the parent pointers from the node that they were assigned to point to root x. So not only do I not have to worry about walking the whole path to reach the root and discover who the root is, I also don't have to worry about doing path compression for the entire path. I just do it for the node x, and by making this recursive call, I will ensure that everyone does it for their respective nodes, which means the entire path would get compressed. So the code for path compression is actually quite compact if we write it this way. We know that this should improve the overall complexity of that whole process of doing a sequence of unions and finds, but I'm not going to discuss the time complexity analysis of the effect of doing path compression because it's really complicated. It's typically done in an advanced undergraduate or graduate course on algorithms. It's not really relevant for interviews. From an interview perspective, what really matters is that path compression effectively makes the average complexity or the amortized complexity of doing a find operation practically a constant time operation. So even though we saw that for a particular call of find of x on x might take time that is say proportional to log of the number of nodes in that tree, but subsequent find operations are going to be really cheap. And so if we take the cumulative amount of work that is being done across all the find operations and we divide it by the total number of find operations, we find that that amortized complexity, or you can think of it as an average complexity of find of x, is practically speaking constant. Okay, it's a number that is less than 5. Now it's not theoretically constant, but again, this is not a university course on algorithms. We are here concerned about what works in practice, and in practice the find operation is going to run in amortized constant time. And so if we have a sequence of n-1 union operations which take order 1 time, and let's say 2m find operations which again take an amortized constant time, the combined work now across this entire union find process ends up being effectively linear. So in practice, if the graph is sparse, for example, the overall work is effectively linear. It's not even n log n. With path compression, the work actually comes down to practically linear time.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your 3 webinar slot today